Hi, this is Parisa. This is assignment 8, behavioral cloning. Um, it's like behavior cloning is a form of imitation learning that is like instead of you trying to learn driving by your own, instead of asking an agent in reinforcement learning to learn something from scratch from random movements, learn that from an expert's point of view. And in this case, our expert's point of view would be deep, deep neural network that looks into these Honda dataset images. So these are a set of images put together that looks like a video. Looks at each of these video frames, and also it knows the some extra information, the steering angle of the car, and regarding that, tries to understand in what look it gets from the window of the car, how it can rotate the steering wheel. So to do so, we are getting a data set from GitHub, and some source code from here, and unzip the data set, and then load the packages required. In this case, we're using Torch, which I'm not very friendly with, but I should get. So I'm sorry, I'm so tired. I'm a little bit slow. And then we select the random seed, and then we make sure that if we have access to GPU, let's use it, because just kind of slows down if not. And here is the architecture of the neural network we're going to use. This is a deep network. The input layer has 3 channels RGB, 66 by 200, so it's like rectangular, as you can see here. And then they're normalized, and then pass through multiple 5 different convolutional layers that have different kernel sizes, and then flattened and passed through 4 more dense layers. Uh, so we want to implement this, and here is the class and video model that we have to do this. We'll initialize these values that there are convolutional layers, and their batch normalizations. Each layer is followed by a batch normalization, and defined by different parameters like kernel size and input output size. And the activation is ReLU, and there are also fully connected layers here that still they are also passed through batch normalization 100%. Okay, no, sorry, 100 connections. I confused it with Keras. And so this helps with decreasing the confidence of the system to avoid overfitting. And then we define the feed forward function using those values we defined up there. By passing the input x, we want it to pass through the convolution 1 with activation ReLU, and 2 and 3 and 4 and 5 uh, con- consequently. Then this reshape flattens it, uh, so flattens the old imaging result to one D array, passing through multiple fully connected layers with ReLU function. The last one is has 10 to 1, so the output, there is one output that has a continuous value. It can be anything because it's the rotating angle, so it can't have any value. That's why we don't have any activation here, uh, just not to limit the output of this layer. The initialized hyperparameters are the batch sizes for train and test, and number of epochs, and the learning rate. In exercise 1, we define the model. What we do is initialize a new model, and initialize the Adam optimization uh, and the parameters we pass to this optimizer. So model is defined here, optimizer in Torch is defined as torch.optim as dot Adam, and then we pass the model parameters to it. So it passes all the parameters that are in the model and also the learning rate that we defined up there. The loss function is also a mean square error loss. We load the train images, angles, and test images and angles from a prepare data function that we downloaded from. Um, so here it is. It should. Oh, it's not. Sorry. So let's see where the prepare data was. I missed that one. Yeah, it should be. Oh, it's in the utils folder. It's in the utils file. So it's one of the functions in utils file that preprocesses the data, prepares it for this task. I don't want to go through the details of it. And and then plots some sample images from it to see how they look like, and define our train data set and test data set, kind of PyTorch compatible, and the data loader loads the data in smaller batches so that we don't need to load the entire data set all at once. We just load them when we want to process them. And so here that is what pictures look like and what this tuning angle would say. Like my guess would be negative looks like at left and positive is right. And the bigger it gets, the more you need to rotate. So I just making sure the GPU is run, and then we move our model to the GPU and then train it, and then prepare the loss collector as zeros for putting the losses in there, so that for each epoch we are saving one loss. And the best loss would be in for now. It means that it's actually the worst possible loss. Initially, we get the worst as the best, so that whatever we get a little bit, even a little bit better than that, becomes the best in the next step. In the next step, until we find the absolute best loss value, and then we start training. Keep track of time, and for the number of epochs, we print some logs out there, and then set the ground truth train and prediction train as empty lists. Here, we want to go through data loader in the training section. So it means that we load a set of data in a small batch, and name it data, and also enumerate makes a BI or batch index to BR index here. So input batch and targets batch are all gathered from the data. And then the ground truth is is our target. So as the ground truth is our target, we just convert it to NumPy, and we kind of keep track of the ground truth for all the uh, batches. And input batch would be moved to the GPU as well as the target batch. And so this permute kind of moves the dimensionality in a way that it looks like first batch size, then channels, then height and width, which is a common thing for Python. I think if we keep the channel in the beginning, it's kind of faster. I'm not sure if I'm right in that aspect, but that's basically what I think is the reason. And we clear the gradient optimizer for each batch to this is okay, yes, to start clean and calculate the output by passing the inputs to the model. So it's kind of straightforward. And then we predict the test value. So okay, and in order to save space, we're moving outputs from GPU. It was on GPU. Inputs were on GPU, so model was also on GPU. So outputs are on GPU. To save some space for later processing of GPU, we move outputs to CPU, detach it, and convert it to NumPy array, and keep track of these outputs of the model that are our predictions. And then calculate the loss based on the difference between the prediction. So we pass the output and what it should be, the target batch. And we squeeze it just, I think there's some dimensionality mismatch, or they might be. Here we need to go to the backward process to update do the back propagation step to update the weights. And to do so, we need an optimizer to calculate the gradients for us and minimizes the loss. And then just to keep a track, we add this loss to CPU and convert it to NumPy from Tensor. Okay, um, that's called loss NumPy. And then we are accumulating the batch loss to late to later after all batches training we get the average value for batch training, and then we print the average batch loss. um, so we print this value to see how it worked, and then we also keep track of this loss, saving it, adding it to train loss collector, and for each epoch it adds one more item to this loss collector until the epochs are finished. And then we also check that if our loss is getting worse, so uh, we keep updating the best loss, saying that if um, our current loss is better than what we had before, just update it and put the average batch loss in there and save it somewhere as bestmodel.pth. And then it is finished. Here we can see like what epoch we are in and what's the average batch loss for each of them. And then we expect it to start to decrease and get lower and lower and lower. As we can see here, we also plot it to better visualize it, and it is getting lower, meaning that it's doing a good job on the training set, but we need to also apply it on the testing set to see how it performs on an unseen data. We disable, okay, gradient calculation do not need the optimizer during model evaluation, basically because we don't want to change the model, we just want to use it to test it and to see how it performs without changing it. So we already trained everything and we don't want to train anymore. We pass the batch of test inputs through the model and we get the outputs, predicted test outputs, and then compare it with the targets test test and see how well it's doing on the validation or test set. So we define the model again and we load it from the saved best model. It's kind of straightforward. Best model to or move it to GPU and using eval, we are preparing it for evaluation. Then again, ground truth for and prediction for test are empty in the beginning. and test loss is 0. And so no grad makes the gradients like freezing it so that it doesn't change. And we again start to load from the data loader batch by batch, and save the data to inputs and targets, and then keep track of targets as ground truth, and then these are kind of repeated. What we want to do here that is not repeated is here it's also repeated, that we pass the inputs to the model function and get the outputs that are our predictions, and we want to compare that with the target batch that we loaded from the dataset directly to see how well we performed and calculate the loss, accumulate it, and average it at the end of all batches, and then keep track of it and write it down. And then we